So we move on to next presentation by Dr. Matthew Flynn. So Matt Flynn is our postdoctoral researcher at CFM, focusing on the Novus project, particularly on plastic recycling, paper cup recycling. So his research interests include synthetic chemistry, polymer chemistry, and polymer processing. Which is finding solutions for the recycling plastics. Great.
Thanks, Pratik. Hopefully you can all hear me properly. We shall see how we go with getting the screen share to work. Okay, should be this one. Right. So I'm going to have two parts to this. The first is just a really high-level overview of plastic recycling and sort of the considerations to take into account and some of the not so obvious factors that come into play. And then the second is going to be just an example of some research we've been doing on recycling coffee cups, which, although they're mostly made paper, there is a plastic lining that makes them really difficult to recycle, and just some of the interesting outcomes we've had from that research. So to start with, I'm just going to look at types of plastic that we work with, the recycling methods used to deal with the waste at the end of life, some statistics in plastic consumption in Australia, and other factors that come into play when recycling plastic. So there's two broad categories of different types of plastic. That is thermoplastics and thermosets. So thermoplastics are long entangled chains. The common description is like a plate of spaghetti. So long chains that when you try and pull them out, they can slide past each other, but they're so long and entangled that they act as a solid mass. And these soften or melt when they're heated. And so this is what enables us to do mechanical recycling on them. And generally they're processed at a high temperature, so they're molten and injection molded or compression molded. Whatever process you're using, it's generally done above the melting point or glass transition point of the polymer, depending on what you're working with. They're typically more ductile, so they stretch when you pull them, typically. And these are the commodity polymers like polyethylenes, polypropylene, PET, PVC, and a whole host of others. The other major class is thermoset polymers. So these are the ones that are the main class of polymers used in composites, for example, and they're cross-linked chains. So still long chains, but they are all chemically bonded to each other, so they can't slide past each other. And this makes them a lot more brittle. They can't stretch as much, typically. And once they are set in place, they don't melt. They don't soften nearly as much as thermoplastics. Once they get to a high enough temperature, they just degrade. And this might be higher than the thermoplastics, or it might be lower, depends on the polymer. And their processing is generally done as monomers or short chains, as you showed us talk earlier. And then they are set into place. And once they're there, you can't really do much with them at the end of their life, in terms of you can't melt them and reshape them. And the major classes of these are things like epoxies, polyester resins, polyurethanes. And the terminology used can get confusing because PET, for example, another name for it is polyester, but then you have your polyester resins, which are thermosets, that also get called polyester, and it all just becomes a big mess depending on who you're talking to, what they want to name something as. A subset of both of these categories, but mostly the thermoplastics, is bioplastics. So this describes plastics that are bio-based, so coming from a bio source, so from plants generally, they could be biodegradable, so they break down in the environment into monomers or into some harmless material, or they can be both of these things. So there's a diagram here of some different polymers that fall into one or both of these categories. So you can have PET or polyethylene or polyamides that are bio-based, but they're not biodegradable. Similarly, there are some biodegradable plastics that are made from fossil fuel sources, such as polycaprolactone, and they are also considered bioplastics, even though they're not. They're still coming from a fossil fuel source. And then the terminology around biodegradable also is a bit nuanced. So they generally are describing plastics that break down during composting, and there's standards for this that they have to be at or above, I think, at 58 degrees. So this is, we're talking about industrial composting facilities. Sometimes they're described as breaking down in soil or in water, and these are at more ambient conditions, 20 to 25 degrees. And these all have different standards. An example for the standards for composting biodegradation or biodegradability is they have to biodegrade by 90% within 6 months. So this is the polymer turning into CO2. 90% of the mass has to be gone within 6 months. And another criteria that they have to meet is that they must have no more of 10% of the original mass that's retained on a 2mm sieve after 12 weeks. So if you compare this to the definition of microplastics, which is any plastic particles less than 5mm, by definition, the biodegradation involves a step that you're generating microplastics. So this can be a problem if they're not biodegrading fully. You end up with just microplastics being generated in the environment. And as well, you can see the difference between 12 weeks, so roughly 3 months versus 6 months. The composting facilities want to get through their product as quickly as possible and turn over as much stuff as rapidly as possible. So if they can get away with it, they're going to cut the times down shorter, and they might not have this biodegradation happening fully. As I said, a lot of these are thermoplastics, so they're also recyclable, but they need to be recycled with like plastics. So if you've got PLA, which is one of the major bioplastics, it needs to be recycled with PLA. So you need to collect and sort your waste quite efficiently still. When it comes to recycling, there's sort of two major categories of it. Mechanical recycling handles the bulk of stuff currently. So this involves taking the plastic pellets, you mold them into your products, then at the end of life, you shred these products and you re-extrude them into pellets, which go back into the molding process. This is a relatively simple process. It has fairly low energy requirements because you just need to, shred and clean your plastic and then remold it, re-extrude it and remold it. And the scale is pretty flexible. You can have small scale, you can have very, very large scale. But this only works for thermoplastic polymers. It has a reduction in quality where the polymer chains degrade and you need to top it up with virgin polymer to keep the mechanical properties there. And you also need to sort and clean your input quite well, because otherwise you just won't get a quality product at the other end. The flip side is chemical recycling. And so this has the products that come out are the same as the virgin polymer, because you turn it back to a monomer, you can refine it, and then you can generate your polymer that's the same quality. It can take relatively low quality input. It doesn't need to be as clean. It doesn't need to be as finely sorted. And it also can deal with thermoset polymers, which mechanical recycling can't do, same for using as a filler in your polymers. The downsides of this is that it's more complicated. It needs a much larger scale to operate efficiently and especially to be economical. Because there's extra steps, it's got higher energy inputs, and also the process itself is a higher energy input. It also typically gets very low yields, so usually 10 to 15% with current technology. So the best approach is really a mix of these, mechanically recycling what we can, chemically recycling what we can't, and then recovering energy from all the rest. There's some statistics here on the plastic consumption in Australia. So the plastics that are labelled 1 to 6 make up about 70% of the thermoplastics used in Australia, and all the rest are just labelled as 7. This doesn't really mean anything. The little recycling arrows around the numbers don't necessarily mean that they're recyclable. They typically would be because they're thermoplastics, but it's just an indicator of what polymer is in there, and the product itself sort of dictates a lot of the recyclability. If they put certain things in there, or there's mixed plastics, it makes it a lot more difficult to recycle. And just at a quick view, you can see that a large portion of the consumption of all these polymers is in packaging, really with the exception of some of the smaller quantities of plastics, so the polyamides and your styrene acrylonitrile polymers are used for other things, and PVC is largely used in built environments, so power cables, some windows, things like that. And PVC also really wreaks havoc on the recycling system because it degrades into corrosive products that deteriorate the whole system. Some of the other complicating factors is just identifying and sorting the plastics. So this is probably the biggest hurdle in terms of, if you're looking at plastic packaging, identifying and sorting the large volumes, which is necessary for mechanical recycling, is very, very costly. And so you need generally quite pure streams like containers for change, or waste systems like what Chunda was talking to us about earlier, where you've got one supplier providing one type of plastic. That really facilitates a good, successful recycling system. Generally, if you mix plastics, they don't mix together nicely. They act like oil and water. So the top right image here, this is 2 different plastics. I think it's polyethylene and polypropylene. And they just kind of, you get bubbles and they really deteriorate the mechanical properties. And a lot of the plastics that are used in packaging are used as mixtures. So multi-layer films, approximately half of the flexible films used in packaging are multi-layer films. PET bottles with polypropylene caps, for example, there's a lot of things like that used in packaging that causes these problems with mixed plastics. And then you've got all the other things that are added, like fillers, plasticizers. Something like 85% of plasticizers are used in PVC. So if you can avoid that, you avoid a lot of plasticizers. But if you've got things like flame retardants, if you can recover them and reuse the flame retardants, it's great. But if you are not sure that they're there, then they're just adding complexity to your system. And you can use compatibilizers to improve the performance of the mixed plastics. So the bottom image shows a compatibilized mixture. You can see the dispersion is a lot better and the performance is improved, but then you've got another thing that you're putting into your waste stream that just complicates things further. Because of this, a lot of the recycling processes are actually better described as upcycling or downcycling, where they're turned into a different product that still has value, but it's not the same product it originally was. So an example is taking PET drink bottles, and if you can't get a high enough quality to turn it back into a drink bottle, they often get turned to carpet fiber. And then when the carpet is at its end of life, it just gets disposed of. So now we're going to talk about an example of sort of a mixed waste stream and what we're doing as a method to deal with it. So coffee cups, we use 1.6 billion coffee cups per year in Australia. If you've seen the War on Waste, they have a tram that they filled with coffee cups and they were driving around Melbourne. This tram filled with coffee cups, we would generate 1 every 20 minutes with the rate of cups that we use in Australia. Despite what a lot of people think, they can't be recycled with our recycling systems. The paper mills would need advanced infrastructure to stop the plastic lining from clogging their refining systems. Some manufacturers have designed the cups that they have improved recyclability, so the coatings come off more easily and things like that. But if you don't know what cup you're getting, what manufacturers made it, you don't know if you're going to be able to put it in your system. And sorting the cups in the first place is quite difficult. Another alternative is biodegradable cups. So WA, for example, has banned the use of regular cups and everything must be biodegradable. But composting these cups, you lose pretty much all of the material value at the end of life. And all you're doing is preventing the litter side of it. And again, if they don't end up in the industrial composters, they just end up as litter or as microplastics. So they are generally phasing out these single-use plastics throughout Australia, but the alternatives that they've recommended are inconsistent and sometimes not even developed. And then this is just one example of the class of liquid paperboard products. So coated paper designed to hold liquids. So cold cups as well, like what you would get at McDonald's or at 7-Eleven. Long life milk cartons and juice cartons, things like your Tetra Pak, they all are the same sort of construction. And wax cardboard is a different coating, but the same problem of high quality paper that could be effectively reused, but it's coated in a material that makes it very difficult to recover. And collectively, these make up 200,000 tonnes of waste per year in Australia. So what we're doing is we are, rather than any of the schemes to recycle this stuff or reuse these materials, which is using them as fillers in plastic or concrete or road base, then once they go there, they can't be reused again. They're just there until that gets sent to landfill. Or for wax cardboard, it's pretty much exclusively energy recovery, so they use it for fuel. We're using the coating as a binder and shredding these things and then pressing them together, and the binder, the coating ends up binding together all of these flakes. You end up with what is technically a composite material, just not the same composite that most of the people in the centre will be familiar with. But also because of the nature of the process, they should be recyclable by just granulating them again and pressing them back together. So we've taken cold cups as the example because it's sort of an intermediate in plastic content of all the products out there that could go through this process. And we just had a look at the effects of some of the different processing parameters. So the temperature, you can see it in the graph here. As you get to high temperatures, you get to better mechanical properties of the ultimate product, but it also starts to burn and really starts to smell quite bad. We also get a decrease in how much water is absorbed at higher temperatures. So this is because the polymer is flowing and it's sort of encasing the paper and stopping that water absorption. And this is, as we see by this correlation, quite closely related to the same properties that are imparting that increase in tensile strength. Then we have the pressure that we're using to press it. So as you can see in the light blue here, the samples get up to a certain density here, and then they plateau. They don't get condensed any further than that, and this is where the tensile strength plateaus as well. When the samples are dried, they don't condense as much, and so they don't have this plateau. But we have a really nice exponential relationship. So you can see on this log-log plot that it becomes linear when it's plotted this way. So there's a really close relationship between the density of these samples and the tensile strength. So the materials that we've produced, they have not the most impressive mechanical properties, but they are in the same range as some of the paneling materials that are used for walls. So gypsum plaster, particle board, those sort of low-cost building materials that are high volume, and we get mechanical properties that are as good or better than them in some cases. So this is a really promising application for really high volume waste material that is quite simple and could also be implemented in regional areas rather than having to process everything in major cities. When we're looking at the mechanical behavior, we get this non-linear stress strain response. So there's no elastic part of the curve. It's constantly curved, and the apparent elastic modulus is constantly changing. So what I've measured here is the tangent modulus, and we can see it starts off at about 2000 megapascals, and then as you extend the material more, it gets less stiff, and at its breaking point, it's all the way down at about 200 megapascals. And then doing a cyclical loading scheme here on the bottom, we can see that when it's loaded and then relaxed, it never recovers back to zero strain. It permanently deforms each time. No matter how little you deform it, it still returns back to a larger strain value than it started out as. But one thing that we see from this is this area between the loading and unloading curves is actually sort of a force dissipation. So it absorbs some of the energy which gets dissipated as heat ultimately. So there might be some applications in damping and impact absorbing and that kind of thing in this material. And this is a similar response to what we see paper. So the paper that's making up the bulk of the material is imparting some of its mechanical properties, even though the bonding is all done through the plastic. So we want to extend this and have a look at different size reduction techniques and see if we can improve the properties further, and have a look at other liquid paperboard products. So see if we can get these to higher waste volume products and deal with more waste. And then look at some other things that might be important for use as building materials, so flame retardants, thermal insulation, acoustic properties, and hopefully develop this as a general application for dealing with this kind of waste material. That's it. So thanks everyone for listening.
Great presentation.